Okay, so today we're talking about section 7.5, and in that we're going to start solving trig equations. And so it's going to bring everything together that we have used so far. Excuse me. Okay, so in this, because we're bringing everything together, we're going to have to really pay attention to what we're being asked and how we can solve that. Because each different type of equation has a different way to go about it, depending on the directions. So, for example, we'll just jump right in. Let's say we want to find all real solutions that satisfy our equation, and our equation will be the cosine of x is equal to this negative square roots of 2 over 2. Now notice here we are being asked to solve and find all of them. Okay, so if we look at our unit circle, remember that the cosine values are the x values. So I'm going to draw a line where negative square roots of 2 over 2 would be. This is x is equal to negative square roots of 2 over 2. The reason why I'm drawing this is because the cosine represents the x factors. Okay, so it intersects our circle at 2 different points. Now we know what these are. There's our first branch, which is 3 pi over 4. Okay? So one solution to this equation is where x is equal to 3 pi over 4. Specifically, this is the first angle I'm talking about. Okay? But we're instructed to find all of them. So any looping around, like say the next one, okay, so if I take 3 pi over 4 and I add 2 pi, the next angle is 11 pi over 4, so that would be the second loop. Okay? That's a coterminal angle. And any multiples of these loops, like another loop would be 19 pi over 4. Okay? And this would just go on infinitely. There's no way for me to possibly write down what all of these answers are. Okay? Also notice that any negative coterminal loop would satisfy, the angle would satisfy that as well. Okay. But that's not the only one. We also have this angle. Okay. And on 0 to 2 pi, this angle here is 5 pi over 4. So now we have a whole other branch to this solution. And so the first one would be 5 pi over 4. But again, any looping, any coterminal angle, so another loop around, if I add 2 pi, we'll get 13 pi over 4. Okay. If I add 2 pi, that's like adding 8 pi over 4. I would get 21 pi over 4. And it would go on and on and on, an infinite amount. Again, no possible way for me to write all of these. And any negative looping as well, any negative rotation would satisfy this equation. Okay. So what we have to do now is not that we have just 1 or 2 numbers, we have an entire set of numbers, and so we need to think about how we can write them. So this first branch here, from the blue, I could rewrite this in set notation and say that it's the set of all x, because our angle's x, may as well call it that, such that, and then we write down the criteria for what it is to belong in this group. Well, the way I do that is I take the first angle, the positive one that's on 0 to 2 pi, it's 3 pi over 4. And then how did I get to the next one? Well, to get to the next one, I added 2 pi, which is 8 pi over 4, and 3 and 8 became 11. And I also did that for the second one, 8 pi over 4, okay, just using common denominators. Now down here I don't need to use the common denominator. What I've done is I've added multiples of pi. Okay. So notice I've left a little space there, 2 and pi, and then the way I denote these multiples is I put in a k. Okay. And then we'll say where k is an integer. So for example, in this one, if we let k equal 1, then we have x is equal to 3 pi over 4 plus 2 times 1 times pi. So that's just your first looping. which is 3 pi over 4 plus 2 pi, which once we get the common denominator, as we've done above, this is 3 pi over 4 plus 8 pi's over 4, which is 11 pi's over 4. Okay. Now if we let k equal 2, then we'd get 2 times 2, which is 4 pi, and then we would come up with 19 pi over 4. So that's, k is denoting that it's a multiple. Okay. Now this is an infinite amount of solutions, but it's only one branch. We also have this branch. So if we want to write this in set notation, it'll be the set of all x, because we just called our angle x, such that x will be equal to our first one, which was 5 pi over 4. But again, any looping, so that's adding multiples of 2 pi, so we can just write that again as well as plus 2k pi, where k is an integer. Okay, so that is how we find all solutions. When we have all solutions, we're going, because this is cyclic, we're going to have 2 sets of answers. Okay. All right, let's look at another example like this. Let's say, for example, we had to solve the tangent of theta is equal to square roots of 3, okay, and we want to find all solutions. Okay. So, well, now I have to think about this. I really have to manipulate this. I would like to find out where, at least on one looping of the unit circle, where this goes, and maybe I could draw that out. So the thing we have to remember is that we can write any number as a fraction by putting it over 1. The reason why I'm going to do this is because when I'm done, I want this to represent the cosine, or I'm sorry, the sine, and this one to represent the cosine. Now, what I can do is, because I don't have 1s and square roots of 3, I can multiply this by a half and this one by a half. I'm just multiplying them by 1 over 1, so I haven't changed the value. And so what our equation now looks like is square roots of 3 multiplied by a 2 is divided by 2, and 1 times a half is just a half. And now I know where this is going to be. This can be, this will be the sine, and this will be the cosine. Now, since we're dealing with a fraction, there's also one other possibility that would satisfy this equation. It could also be negative square roots of 3 over 2 divided by negative 1/2. Okay, so I actually still have 2 positions on the unit circle that I'm looking for. So where is it that this cosine is 1/2 and then up square roots of 3 over 2 happens here, and in the opposite direction, negative 1/2 negative square roots of 3 over 2 happens here. Now the angles where that occurs, then this is pi over 3, as we know it, and this one is 4 pi over 3. So the first angle occurs in the first looping, occurs here at pi over 3. Okay. So if we were to write that down, that would be the set of all theta, because we're using theta this time, such that theta is equal to, well, our first one is pi over 3. Okay. And then I have to think, well, any looping of that would also satisfy all equations, so plus 2k for the multiples and pi. Now the other branch comes here as the set of all theta, such that theta is equal to 4 pi over 3. Okay. So that satisfies this angle. And then any multiple looping of that would also satisfy, so plus 2k pi. Now in this situation, we could actually even condense these two, because what you notice is that these are actually the distance between these two is actually a known value. They are cyclic in and of themselves. The distance between these two is just pi. So it would also be acceptable in this case to write the set of all theta such that, again, starting with the first one is pi over 3, and then every other looping will be just pi units away plus k pi. So you can write these two as simplified into this. So we're using the symmetry of the circle. Alright, so now we have to think about how we're going to solve these if they're angles that we don't necessarily aren't known angles. Okay, so for example, let's find all solutions to the cosine of theta is equal to negative 0.245. Okay, now this is not on the unit circle, right? But well, I mean, it is on the unit circle, but it's not one of our known ones. Okay, so let's use that same trick. Let's draw down the unit circle. We're going to sketch that out. And the cosine values will represent the x values. And it's negative, just not somewhere in between 0 and negative 1. So we'll sketch out that this is where x is equal to negative 0.245. Okay. And as a sketch then, that tells me that I have two places here on the unit circle. And these places we have to identify before we can identify the looping. So the question becomes, how do we deal with that? So I have two places, one here, A, and we'll call this one B. Okay, so the first one represents an angle here. This is A. Okay. And then any multiple looping of that. And the second one comes down here, and it represents, for a positive angle, this one. And any looping from there we also have to take into account. Well, so how are we going to do this? I can just solve this equation. I know that if I take the inverse cosine of both sides, let's see, how shall we do this? I could undo this angle. Now, because the cosine and the inverse, cosine and its inverse are inverses, that will leave us with just theta on the left-hand side. And what will be left on the right-hand side is the inverse cosine of negative 0.245. Okay. This is an angle, okay, and it is an exact value of an angle. If you were to put this in your calculator, you'd get an approximation. Okay? But this is an exact value, and since we won't be using calculators, this is how I'll expect you to write your answer. Now the question becomes, which angle is this? Is this angle A or is this angle B? And so we have to remember what the restrictions for the inverse cosine are. Remember, that's the one that looks like you're wearing headphones. And so we can see then, if this is the range of the inverse cosine, that this angle here, as an exact value, must be angle A. So this is angle A, but then we have to account for any looping of this, so we also need to add plus 2k for the multiples pi. So then how do we find angle B? Well, we have to think about that, right? And for that, we're going to use the symmetry of the circle. Okay. There's a couple angles we know for sure. We know this angle here is a positive angle. This is positive. Okay. We also know all the way around will be 2 pi. Okay. Now, from the symmetry of the circle, the magnitude of the angle in this direction and the magnitude in the angle in the negative direction must be the same. It's just this will be the positive rotation and this will be the negative rotation. But that's an important part here because we can say this part is the same as this part. which means that if I took angle B and I added this, we would go all the way around to 2 pi. Right. And that is how we're going to write our next angle. We're going to use that fact. So what must be true then is if you take 2 pi and you subtract off the positive value A, that will give us the negative rotation here, the inverse cosine of negative 0.245. Okay? That would be angle B. Okay? All the way around is 2 pi. If I back it off this amount, then I will get angle B. Okay? So this whole thing represents angle B. And then we have to take into account the loopings. So it will be plus 2k pi. Now just to go through this again, but in a way that we have seen before, I guess we could revisit our first example. Our first example was where the cosine of x is equal to negative square roots of 2 over 2. Okay. And the way we did that is just by knowing our unit circle. But let's say we'll do it by this inverse cosine method. So again, I'm looking where the x values are negative square roots of 2 over 2. Okay. Right? So I'll have here one place, angle A, and one place here, angle B, that we are looking for. Okay. And then once we have those, we can take the multiples. Okay. So if we solve this equation by taking the inverse cosine of both sides, then what we have here is what we've called our angle x. The inverse cosine and the cosine will undo each other, and we'll just have the inverse cosine of negative square roots of 2 over 2. Okay. And this represents angle A. Why does it represent angle A? Remember, we'll be using the restrictions of the inverse cosine. It looks like the headphones. Okay. So the angle that this inverse cosine represents is angle A, not angle B. Okay. So it represents the angle, let's put this in blue, from here to here. Okay. All right, but we actually know what the inverse cosine of negative square roots of 2 over 2 is. That is 3 pi's over 4. And remember, we're not just looking for that. We're looking for any looping of that. So, because we're looking for all, so this is 3 pi over 4 plus 2k pi, which is what we had before. Now, using the same method, if we're looking for angle B, okay, that's the angle we're looking for from here to here. Okay. So remember, by symmetry of the circle, this angle and this angle must have the same magnitude. So if you take the orange and add this little blue here, we would get to 2 pi. Okay. So now as we're looking for B, okay, well, B then must be the complete rotation 2 pi minus this little bit in blue, which we said was the inverse cosine of negative square roots of 2 over 2. Okay. And then, of course, we would put any looping on it, 2k pi. Okay. But we can simplify this, right? 2 pi minus, well, the inverse cosine of negative square roots of 2 over 2 is 3 pi over 4, okay, plus 2k pi. Okay. And now we can simplify this. This is over 1 and getting a common denominator. Okay. So this would be 8 pi over 4 minus 3 pi over 4, okay, plus 2k pi. Okay. These are not like terms. This k pi is messing that up. And when we simplify these, then 8 pi minus 3 pi is 5 pi over 4 plus 2k pi. Okay. So this inverse cosine method we actually use when we're doing this. It's just we keep these committed to our brain, so we're doing that step in our head. So this is going to take some practice, but we can get it down. Okay? All right, now we have one that can also be confusing anytime we start dealing with multiple angles. So let's find all solutions. Of 2 times the sine of 4x, okay, this is a multiple angle, minus 1 equals 0. Well, first let's just do some algebra and isolate this sine of 4x. So to do that, I need to add 1 and divide by 2 to get the sine of 4x is equal to 1/2. Okay. Adding 1, dividing by 2. Now, let's just stop and think. If it was just the sine of x equals 1/2. Now, in this case, I'm looking for the sine, and the sine are the y values. So that'll hit here. This is line y is equal to 1/2. Those represent the sine values, and it happens at 2 places. Now, again, I'm going to just use my knowledge of the unit circle, but we'll see later that we're actually using the inverse sign here. So we know that this angle is pi over 6, and this angle is 5 pi over 6. Okay. So if we were just solving this, then our solutions would be x is equal to pi over 6, plus then any looping of it, so plus 2k pi. And we would have a second branch from here, where x is equal to 5 pi over 6, and then any looping of that, plus 2k pi. Okay. Now, that's if we were solving this. Okay. This has a single angle, though, and this has 4 times that amount. So it's really then what we have is that it's not that x is just equal to this. 4x's must be equal to this, and 4x's must be equal to that, because of this. So if it was 3 times the angle, we put 3 in here. 3. Okay, and now we can just solve for this. Okay. Because if it's 4x's here, then I can just divide by 4, and I want to divide everything by 4. Okay. That way the 4's will cancel here. Now remember with this one, dividing by 4 is the same thing as multiplying by 1/4. And we could do the same thing here. Again, dividing by 4 is the same thing as multiplying by 1/4, and I divide that by 4. Okay. So then what we would see then, after we reduce this, is that x must be equal to 1 times pi is pi, and 6 and 4 is 24, plus, and then we can reduce this as well. 2 goes into itself once, and into 4 2 times. So this becomes k pi over 2. And that's the first branch. Okay. The same thing will happen over here. We can divide. Those 4's will cancel. Oops. And we'll be left with just x is equal to now 5 pi over 24. And these will reduce again as well. So just k pi over 2. And this is all solutions. So now we have a situation where we found all solutions. It's a set of all x such that this happens. Okay. But now, what if we wanted to solve on 0 to 2 pi? Okay, so notice I put the bracket around the 0 and the parentheses around the 2 pi. Okay. So that means that's just the positive rotation, and if you have a choice, we include 0, not 2 pi. So, okay, what's our first solution? Well, our first solution is when k is equal to 0, then we just get our first one, pi over 4, or 24. I'm going to just work with this branch now, because if k is 0, we get 0 times pi, which is just 0, divided by 2, which is still just 0. Okay, so this is our first one. Now, since we're working in terms of 24, we really might want to rewrite this. This is from 0 to, let's get a common denominator, 2 pi over 1 times 24 times 24. So 2 pi is really 48 pi over 24. Okay, so that'll just help us as we move through this. Okay. So now we're going to let k equal 1. Okay. So what happens there is that we get k is equal to our first one, pi over 24, plus k, which is now 1, plus, I'm sorry, times k times pi over 2. So that is that is equal to pi over 24. And now this is just simple adding of fractions here, plus pi over 2. Okay. But we need a common denominator, so we'll multiply by 12. Okay. And so we get pi over 24 plus 12 pi over 24. And now 1 pi plus 12 pi is 13 pi's over 24. So we take our original and we add 12 pi's over 24. Okay. Now the next one is when k equals 2. Okay. So that is x is equal to pi over 24 plus, now k is 2 times pi over 2. So that's pi over 24 plus, and we get the common denominator. Let's see, so this is 2 pi over 2. We need the common denominator, so we'll multiply again by 12. Okay. So this becomes pi over 24 plus 2 and 12 is 24 pi over 24. And then adding together, now that we have the common denominator, is 25 pi's over 24. This is our third angle. Notice that 25 pi over 24 is nowhere near 48 pi over 24. So we keep going. And if we let k equal 3, x is equal to pi over 24 plus k, but we're going to let k equal 3 times pi over 2. And now it's just straight algebra. Actually, it's just arithmetic, really. Pi over 24 plus 3 pi over 2. We need a common denominator. So we'll multiply by 12 and by 12 to get pi over, this should say pi up here. Pi over 24 plus 3 and 12 are 36. Pi is over 24. Then 36 and 1 is 37. Pi over 24. Okay. Now this is still smaller than 48 pi over 24. So we can do it again. If we let k equal 4, then we get x is equal to pi over 24 plus, now k is 4 over pi, times pi over 2, which is pi over 24 plus 4 pi over 2, getting a common denominator, multiplying by 12. We have pi over 24 plus 48 pi over 24. Then pi and 48 pi's is 49 pi's over 24. And here we can stop. Okay? 48 pi's over 24 is larger than 48 of them. So 49 is greater than 48. This is outside of the interval that we're looking on. So these are our first 4 solutions. So these 4 solutions come from this branch. Now, we would do the same thing, except we would start with 5 pi over 24. We won't do that now. I'll just tell you what you should come up with. From this branch, we'll get, the first one is 5 pi over 24, and then we're adding multiples of pi over 2 to get to 17 pi over 24, 29 pi over 24, and 41 pi's over 24. Okay. So in this case, we have 8 solutions. These 4 plus these 4. So with the multiple angles, it's actually much easier to solve on for all solutions and leave them as such. Okay. But we'll also be solving on 0 to 2 pi. Okay. So let's move on to different techniques that we can put into this. Okay. Say, for example, let's solve on 0 to 2 pi again. And say we had defined 2 cosine squared of x plus cosine of x is equal to 1. Now factoring will work, we can factor with cosines, right, with trig functions. So notice this is of the form, if we let u be equal to the cosine of x, well then u squared is cosine squared of x. Okay. So I can substitute these in here to get 2 cosine squared, well cosine squared is u squared, plus the cosine of x, which is just u, equals 1. And from here we can see that it's quadratic. Okay. This is quadratic in u squared, in u. This is quadratic in cosine. But this represents that. So if we were to solve this one, we'd get 2u squared plus u minus 1 equals 0. And now this will actually factor. So we get 2u and a u, and we need 1 and 1 plus and minus. So if we were to solve from here, we could split them up, and we know that 2u minus 1 must equal 0, or u plus 1 equals 0. So u equals negative 1, or u is equal to 1/2, adding 1 and dividing by 2. Okay. But our goal was not to solve for u, our goal was to solve for x, okay? And u is the cosine of x, so we either have that the cosine of x is equal to 1/2, or that the cosine of x is equal to negative 1. And now we can solve, just drawing a little sketch for myself, the cosine of x being 1/2 comes here. This is the line x is equal to 1/2. And so there are 2 solutions here. This first one occurs at pi over 3, and the next one is at 5 pi over 3. Now where is the cosine of x equal to negative 1? Well, remember the cosine being the x value, negative 1 happens here, so this is the line x is equal to negative 1, and it intersects the circle in one point, and that point is specifically at pi. So in this case, on 0 to 2 pi, we can do a u substitution and factor, and find out that there's actually 3 solutions to this. So when we have trig functions, remember with quadratics we'd only get 2 solutions, but we can get more than 2 solutions when we are solving trig functions that are quadratic. Okay. Notice if you didn't want to do a u substitution, I could have just factored straight away here. Well, first I'd have to rewrite this as 2 cosine squared x plus cosine of x, and then minus 1 equals 0, because if we're going to factor, everything needs to equal 0. And then I could have just written it as 2 cosine of x minus 1 and the cosine of x plus 1. I didn't have to do this use substitution. Okay. Then when you'd split them up, you'd come down and get 2 times the cosine of x minus 1 equals 0, or the cosine of x plus 1 equals 0. It will all come out to be solving these, and we have these solutions. Alright, let's do another one where we factor. Okay, so for example, let's say we had to solve 3 sine squared of x equals the sine of x. Okay. Now again, let's factor in when we have anything equal to 0, we can factor it. So, well, not anything, but when we are going to try and factor, we like to have it equal to 0. Okay. And now I can factor out a sine of x because it's greatest common factor. Okay, so if I pull that out, we have the sine of x, and now what's left behind is just 3 times the sine of x minus 1. Don't forget that minus 1 equals 0. Okay, so it's either that the sine of x is equal to 0, or that 3 times the sine of x minus 1 equals 0 by the zero product property. And if I add 1 and divide by 3, we really have that the sine of x must be equal to 1/3. Okay. So we're getting closer. Our goal is to get to x, and now we know what the sine of x should be equal to. So from here, if the sine of x is to be equal to 0, well, that's where the line y equals 0 comes in. It intersects the circle at 2 points. So 2 values that we have, and let's solve this on 0 to 2 pi. Here it happens at 0, and over here happens at pi. So that's 2 angles. Now, this is not an angle that is known to us on the unit circle, but that's okay. We can still use our methods that we've learned. Okay, so here's the unit circle. I want the sine of x to be equal to 1/3. This is approximately a half, so a third's somewhere in here, let's say. This is where y is equal to 1/3. It's going to cut the unit circle in 2 places. So I will have 2 angles. Let's call this one angle A, and this one angle B. So doing as we have done before, let's take the inverse to undo it. Okay. When we do that, we'll get x is equal to the inverse sine of 1/3. Okay. So then the question becomes, well, which angle is that? Is that angle A or is that angle B? And so for that, we're going to also have to remember the restrictions of the inverse cosine. Remember, it goes positively from here, that this is pi over 2, and then it goes in the negative direction, that this is negative pi over 2. Okay. So the angle that this represents is angle A, because it's within the restrictions. Also notice that this must be a positive angle, because we go from 0 to pi over 2. If it was down here, it would be representing a negative angle. And so, maybe I should label this one in blue. Okay, so that represents this angle from here to here. Now we're looking for the second angle B, and that angle represents from here to here. Because we're looking on 0 to 2 pi, we want that positive angle. So again, the question becomes, how am I going to find out specifically what this angle is? And for that, we have to use the symmetry of the circle. Okay. I know that the magnitude of this angle must be equal to the magnitude of this angle. Okay. So that is, if I took the orange and added that blue part, I would get to pi. So angle B is x is equal to pi, and now I'm going to subtract off this little bit, which is a positive angle, the inverse sine of 1/3. That's angle B. I guess that should really be an orange. I hope that makes sense. Right? These two must be the same. We know from here to here all the way around is pi. So if I take pi and I subtract off this little bit, the remainder will be the orange. Alright, let's do another one where we find all solutions. Okay, so for example, if we have 2 times the sine of theta is equal to negative root 2, let's isolate the sine of theta by dividing by 2, so we get the sine of theta is equal to negative root 2 over 2. Okay. We want to find all solutions. Okay. So let's find out where on the unit circle that falls. Okay. Now the sine is the y values. I want them to be negative root 2 over 2, so it cuts the circle in 2 different places. So these are the 2 angles that I'm concerned about. And the angle that happens here is at 5 pi over 4, and this angle is 7 pi over 4. We know this just from using the unit circle. So what we could say then is that this is the set of all theta for the first branch, such that theta is equal to 5 pi's over 4. Okay, so that would be an angle from here to here. Would be our first, plus 2k pi. Okay. Then we also have the angle that would come over here, and I just take the first positive one, so that comes here. So that orange branch is the set of all theta such that theta starts at 7 pi over 4, but then I add the 2k pi for any multiple of it. Okay. Now let's do this using, not using our knowledge of the unit circle, but using the inverse cosines, or inverse sines. Okay. So now we'll just pick up from where the sine of theta is equal to negative root 2 over 2. Okay. So drawing the unit circle, here's the line y is equal to negative root 2 over 2. Again, I have these 2 angles. I'll call this angle A and angle B. Okay. So now we can take the inverse sine of both sides. When we do that, we'll find that theta is equal to the inverse sine of negative root 2 over 2. Okay. And then we have to ask ourselves, which angle is this? Okay. Is this angle A, which starts here and comes all the way around, or is it angle B, which starts here? Okay. And the confusing thing about this is that this angle, as it's written, is actually not A or B, specifically as we are looking for them as I have drawn them. So here is why. Let me explain to you. Okay. The inverse restrictions, okay, go on this side of the circle. Okay. But remember, up top it goes from pi over 2, and then when you drop below here, you actually start measuring in negative angles. And let's remind ourselves that we're solving on 0 to 2 pi. That is, we are looking in the positive rotation. Okay. So the inverse sign of negative root 2 over 2 is actually equal to negative pi over 4. And that's not the angle we're looking for because we're not solving in the negatives, we're solving on a positive rotation. Okay? But that's fine, okay? Because what we can do then is I can just add a multiple of it. Okay? So this angle is the negative pi over 4, right? This is negative pi over 4. So if I want to get the blue angle, I just need to add 2 pi here. Okay? So plus 2 pi, which by the way is the same thing as saying 2 pi minus pi over 4. Okay? And then getting our common denominator times 4, we have 8 pi over 4 minus pi over 4, and we get 7 pi over 4. Okay? Which is specifically what we said here. We just used the unit circle. Okay? This is an important point to make, though. Remember, this is negative, and it'll make more sense when we come home. So we're going to have to compensate for that by this angle is coterminal to the one that we're looking for on 0 to 2 pi. Okay. Now, how am I going to find the orange? Okay, because this was angle A. Now we need to find angle B. So we know then that this little portion has to be equal to this little portion. I also know from here to here is pi. Okay. So if I could take pi and then move forward that extra little bit, then we would be to angle B. Okay. So in angle B, we actually take pi, and we want to add to it this inverse sine of negative square roots of 2 over 2. Now we have to be careful, though, because what is the inverse sine of negative root 2 over 2? Well, we just said here it's negative pi over 4 from above. So what I've actually said here is that when I add a negative, I'm really subtracting, so it would be pi minus. So we have to compensate for that. And so we need to keep the absolute value here, because then we can have pi plus, well, the absolute value of negative pi over 4 is pi over 4. And this would get us to, let's see, 4 pi's over 4 plus 1, which would be 5 pi's over 4. Which is what we were looking for here. So take a minute to try and understand exactly what I've said here, because it's going to become more confusing. But we'll just have to remember that the inverse sine, if you're down here, you're going to come back with a negative angle, and so we're going to need to be adding absolute values. We'll do another one. Okay. Now, we can also solve things graphically. Okay, so like if we had 2 times the sine of 2 theta is equal to the square root of 3. Okay, let's do this on 0 to 2 pi. Okay. So again, we're going to get this multiple angle, so we're going to get a lot more that we have to deal with. Okay, and we can solve for this. We want to isolate the sine. So it's the sine of 2 theta is equal to square roots of 3 over 2. Okay. Now let's use our same trick. If it was, whereas the sine of theta is equal to square roots of 3 over 2, okay. So the sine, this is when the y value is equal to square roots of 3 over 2. Happens at 2 places, once here and once here. And we know this angle to be 5 pi, pi over 3, and this one to be 2 pi over 3. Okay. So now let's solve this, if this were the case and we were doing all solutions, then we would have theta is equal to the first branch, pi over 3, plus any looping, that plus 2k pi. And our second branch would come from here, which is 2 pi over 3 plus 2k pi. But that's not what we have. We don't have a single angle in here. We have the double angle, so it's that 2 theta must be equal to these two. And then we can solve by dividing by 2. And here it's easier to remember that dividing by 2 is the same thing as multiplying by a half. Same here. Divide by 2. Okay. In this case, our 2's cancel everywhere. So what we would get is theta is equal to pi over 6 plus k pi. Okay. It would be all of those. Or our second angle from this branch, let's see, the 2's will cancel, and we're left with pi over 3 plus k pi. Okay, where k is an integer to represent the multiples. Now, we can run through and we can let these k pi's, like k equals 0, k equals 1, k equals 2, etc., until we're outside of our range that we're looking for, the interval that we're trying to solve on, which is 0 to 2 pi. Now, here's a way we can do it graphically. Okay. So now, let's graph y is equal to the sine of 2 theta. Okay. So remembering what 2 theta is going to do is that it will shrink the amplitude, or not the amplitude. The amplitude will stay the same at 1. Okay, so it'll go from 1 to negative 1. It's not moving up or down or left or right, but this 2 will change the period. Okay. So 2 pi divided by 2 is just pi. That means it will complete one cycle in pi. Okay. So the main part would be, now half of that is pi over 2, and half of that is pi over 4. And then we can count it out. Pi over 4, 2 pi's over 4, 3 pi's over 4, 4 pi's over 4. So one cycle of this, the sine starts, middles, ends at 0. Then it'll peak at 1 and valley at, it'll peak at 1 here and then valley at negative 1 here. Okay. So this is one cycle. Which is fine, but I'm not solving on 0 to pi. I need to solve on 0 to 2 pi, so let's put in another cycle. So this would be 2 pi, then we'll half of that, and then half, and then half, okay? And you can just count it out if you would like. Okay, so 1 pi over 4, 2, 3, 4 pi's over 4, 5 pi's over 4, 6 pi's over 4, which reduces to 3 pi over 2, and 7 pi over 4, and then 8 pi over 4, which reduces to 2 pi over 2. Okay. Then sine start, middle, and ends at 0. It'll peak at 1 and valley at negative 1. And so here is the sine function, 2 cycles of it. Of course, it goes on forever in infinite directions, but we are just concerned about here. So now we can put in square roots of 3 over 2. Okay? Square roots of 3 over 2 is less than 1, so let's say this is the line y is equal to square roots of 3 over 2. Okay? And what that shows us then is that we have 1, 2, 3, 4 intersection points, which means we are going to have 4 solutions. Okay? So if we let k equals 0, well, this is going to be really easy, right? If k equals 0, it has to be the first angle right here, and that angle is theta is equal to pi over 6. Pi over 6. Okay. Now the next one comes from here, and if k is 0, then this term goes away. So the very next angle here is theta is equal to pi over 3. Now the next one will come from here. We just simply have to add pi. Okay, well pi plus is just 6 pi's over 6 plus 1 pi over 6. The next one must be 7 pi's over 6. Okay? So that's pi units apart. And this will also be pi units apart. So over 3. So 3 pi over 3 plus pi over 3. This one's 4 pi over 3. And notice I knew then I could stop there because I didn't have to go and let k equal 2 and find out it was too big, because I see from the graph that I only have 4 angles where that will be. Alright, let's do some more factoring. And so we can solve equations with tangents and cosecants and all sorts of stuff too if we want. So the tangent minus 2 times the sine of x, tangent of x, is equal to 0. And let's solve this one on 0 to 2 pi. So we can see that there's a common factor of a tangent on both of them. So I'll pull out that tangent, and then I'm left with 1 minus 2 sine of x equals 0. Now we're still just doing algebra. We'll split them apart by the zero product property. So it's either that the tangent of x equals 0, or 1 minus 2 times the sine of x equals 0. So 1 is equal to 2 times the sine of x, so 1/2 is equal to the sine of x. We've done this multiple times now, so x is equal to pi over 6 and 5 pi over 6. Okay. Question about the tangent of x equals 0. Okay, so remember that's going to be, we can write anything as over 1. But also, if we had 0 over negative 1, that would still be 0. So why I bring that up is, remember, this is our sine, and this is the cosine. And so we actually have two possibilities. So where is the sine 0? Here, and the cosine is 1. So we get one answer here, and that is just 0. The second possibility is where the sine is 0, but the cosine is negative 1, and that happens here at just pi. So we get x is equal to 0 and pi. So in this case, we have 4 solutions. Okay. Now, sometimes we're not going to be able to factor. Sometimes we're going to have to do other methods. So let's say we had to say factor sine squared of x minus cosine squared of x minus the sine of x equals 0. So now this is 3 terms, and there's nothing common. I can't factor anything out and then use the zero product property. And I would like to have an equation that was all in just a single variable. Or, well, it's in a single variable, but in a single trig function. And so here's where we're going to use identities. I know that the sine squared minus cosine squared can be written in multiple different forms. One of them is 2 sine squared of x minus 1. And then from here we'll just bring down minus sine of x equals 0. Okay, so you can use identities. Now when we do this, we're going to have to look for extraneous solutions, but we'll handle that. Okay, now this is just quadratic, so this is just 2 sine squared of x minus sine of x minus 1 equals 0. If you want to think about it in a u substitution, this has the form 2u squared minus u minus 1 equals 0. So this is going to factor into 2 sine of x and a sine of x. I need a 1 and a positive 1. If this is going to be negative, I need a negative 2 here and a plus 1 there. Okay. Same thing would happen over here. 2u plus 1 and u minus 1 equals 0. Now from here I can split them apart. So from here we'll get that the sine of x is equal to negative 1/2. And from here we get that the sine of x is equal to 1. So looking at our unit circle, where is it the sine of x is equal to 1/2? Negative 1/2. Happens here and here at 7 pi over 6 and 11 pi over 6. And where does the sine of x equal 1? Just at one point up here. And x is equal to pi over 2. Okay. You may need to look for extraneous solutions. That is, if we plug these all back in, they have to equal 0. It has to make the equation true. Okay. In this case, I've checked them before, and these all actually work. But anytime you do a substitution and change things around, you need to look for an extraneous solution. Okay. So remember, multiple angles are going to cause us some problems. So here's another way to deal with them. If we have the sine of 2x's minus the sine of x equals 0. Oh, and by the way, we were doing this one on 0 to 2 pi. Okay. Otherwise, we'd have to add in the multiples. Okay. So let's also do this one on 0 to 2 pi. Now the problem here is, again, this double angle, and so that's going to be a problem. If I move the sine of x over, I'm going to have the double angle equals the single angle, and I could do some graphing, but it's going to get kind of confusing. What I can do is I can use an identity. I know that the sine of 2x is the same thing as 2 times the sine x times cosine x. Then I just copy the rest of the equation. Minus sine x equals 0. What that allows me to do is then I'm able to factor out this sine of x because it's the greatest common factor. Then I multiply that by 2 times the cosine of x minus 1 equals 0. And now we can split it up. From here we see that the sine of x is equal to 0, or from here we'll get the cosine of x is equal to 1/2. We just solved this. We know that the sine of x is equal to 0 at 0 and pi. And for the cosine of x being 1/2, that's the line x is equal to 1/2. We get here and here. So x is equal to pi over 3 and 5 pi's over 3. And I suppose we should check these. Okay, so let's do that. Well, we have to check all 4. Okay, with 0. Is it that the sine of 2 times 0 minus the sine of 0 equals 0? Okay, so 2 times 0 and the sine of 0. Well, sure, that's just the sine of 0 minus the sine of 0, if that works. Okay. Let's check pi. Is the sine of 2 times pi minus the sine of pi, does that equal 0? So here's pi, and here's pi. Okay, well, the sine of 2 pi is 0, minus, and the sine of pi is also 0. So yes, 0 equals 0. So that's good. Now let's check pi over 3. putting it into the original, leave the sign of 2 times, I'll put in pi over 3 minus the sign of pi over 3. And does that equal 0? Okay. Well, the sign of 2 pi over 3, the sign of 2 pi over 3 is just square roots of 3 over 2. Okay? And then we can subtract off the sign of pi over 3, which is also square roots of 3 over 2. So that equals 0. Okay. So that one checks. And now let's finally do 5 pi over 3. So it's the sign of 2 times 5 pi over 3 minus the sign of just 5 pi over 3. And we're wondering, does that equal 0? Okay. So 5 pi over 3. Okay. Yeah, this should have been in orange. 5 pi over 3. Okay. So this is the sign of 10 pi's over 3 minus the sign of 5 pi's over 3. Okay. So let's find the coterminal angle. 10 pi over 3 is larger than 2 pi. So if we subtract off 2 pi over 1 times 3 times 3, getting a common denominator, that's 10 pi minus 6 pi over 3. So this is the same as 4 pi over 3. So is the sign of 4 pi over 3 minus the sign of 5 pi over 3. Okay. So now we need to look. Okay, the sign, let's see, 4 pi over 3 is here, and 5 pi over 3 is here, and the sign of this is negative square roots of 3 over 2. Negative square roots of 3 over 2. So is negative square roots of 3 over 2 minus from the equation minus square roots of 3 over 2, does that equal 0? Yes. Negative square roots of 3 over 2 plus square roots of 3 over 2 does equal 0. Okay. So these are all good solutions. But anytime we do a substitution, we need to make sure that we're checking. Okay, now let's go back to working with that inverse sign, which is going to give us some problems. Okay. So, for example, let's just pick something very simple. The sign of x is equal to negative 3/5, and let's do it on 0 to 2 pi. So in this case, the sign is already isolated, so let's remember how to do this. We'll scratch out the unit circle. Negative 3/5 is somewhere down here. Okay, it's less than negative 1, so we'll say this is the line y is equal to negative 3/5. And it's going to cut in 2 places. We'll call this angle A, and we'll call this angle B. Now remember, we're looking for the angle because we're solving on 0 to 2 pi. Angle A is this angle all the way around. And angle B, because we're solving on 0 to 2 pi, is from here to here. So if we take the inverse sine of both sides, what we'll get then is just that x is equal to the inverse sine of negative 3/5. And then we ask ourselves, is that angle A or is that angle B? And then to do that, we have to remember what the restrictions of the inverse sine is. They go from positive angles at pi over 2 to negative angles at pi over 2. So it turns out this angle is actually negative, and it is neither A nor B, okay, because we're looking for positive rotating angles. So this angle is actually right down here, okay, and it is coterminal with our angle A. So to get to A, I would just have to add, notice that these two together, the blue angle plus the green in magnitude would be 2 pi. So you can think about this then as adding 2 pi for the blue angle, okay, plus 2 pi, okay, because this is negative, so this is angle A. Alright. Now from here to here must also be the same in magnitude. Okay, now this is a negative angle, right? But the magnitude here and here must be the same. Okay. And when I start talking about magnitude, I need to start talking about the absolute value. So if we want to talk about angle B, which is in orange, what I could do is I could go to pi and then add this magnitude. So I need to take pi plus the magnitude, and the way I'll denote that is that I need the absolute value here. And that will get us to angle B. Okay, let's try and solve this one. Example. If we have the cosine of x is equal to 4, now we could just proceed through here and say, okay, I'll take the inverse cosine, so x must be equal to the inverse cosine of 4. However, let's think about, we have to start thinking about whether these angles exist. If I was to use this method of looking at the unit circle to try and figure out where the intersection points are, here is the point 0, 1. Okay. Here's the point 1, 0. Okay. So what I would be looking for is the line x equals 4, which is way out here, and we see that this line and this circle never intersect. This angle does not exist, because remember, it can only take in values from -1 to +1 into the inverse cosine. Okay, so this doesn't exist. Alright, let's do one last one that pulls everything together. Let's make it 5 cosine squared of x plus 3 cosine of x minus 1 equals 0. And we'll do it on 0 to 2 pi. And remember, we're not going to be using a calculator. Turns out that this function is not going to factor, okay, but it is quadratic. Okay, this is a quadratic form. So what we can do is we can use the quadratic formula. Now it's not quadratic in x, it's quadratic in cosine of x. Okay, so a is equal to 5, b is equal to 3, and c is equal to -1. But it's quadratic not in x, but in cosine. So it's not that x will equal this, it's that the cosine of x will equal this. So now -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And now we can just simplify. This is -3 plus or minus the square root of 9 plus 20 over 10, which is equal to -3 plus or minus the square root of 29 over 10. Okay. So what that means is that we have two equations to solve. We need to solve for the cosine of x is equal to the negative branch, -3 minus square roots of 29 over 10, or the cosine of x is equal to -3 plus square roots of 29 over 10. So to solve this, what we would do is we would take the inverse cosine of both sides. But what we just saw is that if the numbers we put inside of here, so in this case this -3 minus square root of 29 over 10, if that number gets larger than positive 1 or more negative than negative 1, we're in trouble. So that is, we have to ask about this existence. Do these angles even exist? Now, if it was just negative 3 over 10, I would say absolutely, because this is not as large as negative 1, and the same here. So really the problem is coming down to this negative square roots of 29. And we don't have a calculator, so let's figure out how we can do this. Well, what we have to know then, we know this is true. On a number line, we know that 25 is less than 29, and 29 is less than 36. We know this to be true. So what we can do then, what also has to be true, is that these square roots must also follow that way. Now, why did I do that? Well, because the square root of 25 is 5, and the square root of 36 is 6. So, we're going to use this as an approximation. That is, the square root of 29, we are subtracting a number that's 5 point something. So let's think about that then. So if we're subtracting negative 3 minus 5 point something divided by 10, well, that's going to be negative 8 point something over 10. And now this number is still less than negative 1. Right? Negative 8 over 10, a little bit more. If it was negative 9 over 10, it's still less than negative 1. So this angle exists. This one works. What about over here? Now negative 3 plus 5, and a little bit more over 10. I hope you can see this. If it was just negative 3 plus 5, it'd be negative 2 over 10. Okay. Even if this number is really close to 6, so minus 3 plus 6 would be 3 over 10. So these both exist. Okay. So both of these exist. So now what we have is we have a solution from here and here. I'm just going to take the inverse cosine of both sides. The first one is x is equal to the inverse cosine of negative 3 minus square roots of 29 over 10. And the second one is x is equal to the inverse cosine of negative 3 plus the square roots of 29 over 10. Now let's draw our unit circle so we can see how many solutions we'll have. So we said that this number was approximately negative 8 tenths. And in this one we said was approximately 3 tenths. Approximately. Alright. So the inverse cosine of negative 8 tenths. So that's not quite negative 1. So it's going to cut the circle here and here. We'll call this one angle A and this one angle B. So we're still looking for two angles. From this side, we had a positive 3 tenths. So that's going to be closer here. But either way, we're still going to get two solutions. We'll call this one C and this one D. Angle A goes from here to here. And angle B goes from here to here. Okay, so we'll start with this one. So which is this? Is this angle A or is this angle B? Okay. So remembering the restrictions of the inverse cosine, which is much nicer because it stays positive than the inverse sine, goes from here to here, from 0 to pi. Okay. So this is angle A right here. So the question is, how do we find B? And remember that the blue angle of magnitude must be the same in magnitude of this direction. Okay. So if I put these two together, I would, the orange plus this blue in magnitude, I would have 2 pi. So if I take 2 pi and subtract off our blue part, which is the inverse cosine, I would have angle B. Okay, so far we have angle A and angle B. And now we can do the rest. So over here, angle C goes from here to here. Angle D is the positively rotated one, from here to here. And the restrictions of the inverse cosine go from here to here. So the angle that we have found right here, this one is angle C. And now to find D, remember that this magnitude must be the same as this. So the orange plus the blue would be 2 pi all the way around. So if we take up 2 pi and subtract off the original angle that we found, as an exact value, we have angle D. Okay. I need you to practice these by hand and make sure that you do them by hand. You'll be asked to demonstrate this on your exam without a calculator. So I think that's the hardest part here. So make sure that you're emailing me if you have any questions.